Today's topic is machine learning. And I picked machine learning for a couple of reasons. One, it's really a hot topic in computer science now. It's kind of everywhere. You interact with it in your daily life, whether you know it or not. Some of the ways that you interact with machine learning are more obvious than others. I think everybody probably knows that when you say, hey Siri or Google and talk to your phone, that on the other end of that connection, there's a machine learning algorithm whose job it is to figure out what are the words that you're saying, what do they mean in that order, and how should I respond? Um, you know that when you get in a Tesla or a BMW or some high-end car, heck, even Subarus do it now, and put it in auto drive on the road, that there are machine learning algorithms taking the input of all those sensors, cameras, radar, lidar, all the inputs that are coming in, and deciding, should I slow down, should I speed up, turn left, turn right. All of those things are machine learning algorithms. Some are not so obvious. If you go to the bank and ask for a loan, odds are that 15 years ago, of course, it would be a human being who looks over all of that financial data and decides whether you're very likely to repay that loan or not. But today, it's as likely as not that the first view of that data that you provide to the bank is going to be taken by some machine learning algorithm, and it's going to make a recommendation. Now, of course, there are humans involved in the process, but more and more algorithms are involved in evaluating things like medical data for diagnosis, financial data, and all kinds of other decision-making processes that are driven by data are actually done by machine learning algorithms. And right now, as we speak, there are enormous numbers of machine learning algorithms dedicated to identifying potential drugs that might bind to the COVID-19 virus, that are trying to track using cell phone data and other information sources, tweets and internet connected thermometers, trying to track the progression of the disease, that are modeling how the disease is likely to progress under a bunch of different scenarios, and so on and so on and so on. So in medicine, in finance, in technology, everywhere you look these days, you find machine learning. And what I want to talk about today is a little bit about why that is, what's happening, what makes it so popular right now, and if you're interested in it, what you might do to get ready to start studying machine learning. And in fact, I'm going to be I put this under a little bigger of an umbrella besides just machine learning. I want to talk about data science in general, which involves a lot of different areas, all of which have the common aspect that they involve learning from data. They either involve helping humans to learn from data or teaching machines directly to learn from data. And some of the courses and areas that we offer at Wright State in this include machine learning, artificial intelligence, classes in analytics, data science, pattern recognition. You'll hear the term informatics. Sometimes you'll hear the term big data directly. And I have this little thing about Glassdoor down here because a quick search on Glassdoor, which is a job finding site, reveals that as of the time that I did the search, which was about 2 weeks ago, data science was the #1 job category on the entire site. Some things have changed in the last couple of weeks. Obviously, nurses, delivery people, all specific to COVID-19 kinds of things. But over the last few years, the trend has been very strong that data science has been one of the top job areas, both in terms of salary, number of openings, growth potential, the interestingness and satisfaction of people working in the field. In a lot of different ways, data science is kind of topping the charts. And in fact, for the last few years, I've been the graduate director of the program here in computer science and engineering, and I've probably had more queries from students interested in graduate work in data science than just about any other topic. This is a popular area. And I want to just kind of quickly note that when I'm talking about machine learning today, I'm going to be talking about one specific branch. The two areas that largely involve teaching machines to learn from data are artificial intelligence and machine learning. Pattern recognition kind of falls in there, analytics a little bit, but that's more human and engaged. But I want to distinguish between the world of AI and the world of machine learning right now just a bit. Some people define these in different ways. When I look at the two of them, what I think of for artificial intelligence is that it largely involves trying to teach computers things that humans know. And the way that you do that in artificial intelligence is largely figuring out how you can encode things that humans know in a way that computers understand. Computers obviously don't speak English. So we can't tell them things like monkeys have tails and monkeys live in trees and monkeys have ears and monkeys have fur because they don't understand language. So we have to figure out ways to encode that. And then we have to sit down and think about what are all the things we know about monkeys, or maybe scour the web or go through Wikipedia and determine what are all of the things that we know about monkeys so that we can teach an algorithm to understand what a monkey is and be able to answer questions about whether something is a monkey or not. Machine learning, on the other side, is very much driven directly by the data. We create an algorithm. And the intention of this algorithm is eventually, the intention of this program is to be able to tell us whether something is a picture of a monkey or not a picture of a monkey. But the way that we train it involves not telling it anything that we know or think we know about monkeys, but simply giving it lots and lots of examples. So we might say, here's a picture of a monkey, here's a picture of a monkey, and I didn't put it in here, I really should have, negative examples too. Here's a picture that's not a monkey, and I give it a picture of a motorcycle. Here's a picture that's not a monkey, and I give it a picture of a cat. And then I give it pictures of monkeys from every conceivable position, orientation, species, background, and everything else. And the objective is to build a program that can look at all of this data. And then I can go and say, with a new picture, is this a monkey? And that picture will be able, that algorithm will be able to say, sure, yes, I think with this degree of confidence that it's a monkey, or no, that really looks like a house cat to me. It doesn't look like a monkey. Some similarities there, but definitely some differences. So how do we possibly go about doing this? How do we go about teaching a computer what the difference is between a monkey and a house cat? I think I'm going to skip this slide and come back to it in a minute and talk about this first. So in order to understand how machine learning algorithms work in the general sense, what I would like to do is walk you through the simplest machine learning algorithm that I know of. And this is a real in-use machine learning algorithm. This is not a fake toy algorithm that's only taught in classes but never gets used in the world. This is a legitimate machine learning algorithm, but it is by far the simplest. And then we'll talk a little bit about the weaknesses of it and how we might make it a little bit better. So if you step back a little ways from your computer and squint your eyes a little bit, you can probably recognize that image on the left as a really, really low resolution picture of Abraham Lincoln, former US president, right? And you can do that even though it doesn't look a lot like Abraham Lincoln when you kind of look at it up close and with clear eyes. But when you squint and back up, it does. And that's because the human brain is an outstanding pattern recognizer. It is really good at recognizing, even in the case of, it's really hard to say, where's the nose, where are the eyes? You can kind of see the beard on this one, but that's about it. And yet you squint a little bit, and sure enough, it's pretty obvious, hey, that's Abraham Lincoln. Brains are great at this. Computers tend to not be so much. Now, first of all, computers can't process images directly. As we know, if you're in computer science, and as you will know if you decide to come and study computer science, one of the first things we're going to talk about is computers only speak one language. The only language that computers know is binary. Zeros and ones. That's it. Everything is operated off of zeros and ones. But you can use those zeros and ones to represent other things. And one of the most natural things that computers are good at working with is numbers. Computers can do math much, much faster than humans can do math. They can do very complicated operations. And so if we can convert things into numbers, we can probably come up with a way to build some statistics models that allow us to understand the difference between pictures of humans and maybe pictures of cats. So if I was going to develop an algorithm whose job it is to tell me if something is a picture of a human being or not, one of the first things that I would want to do is encode that data. So I want to convert this low resolution picture of Abraham Lincoln into a set of numbers. So the first thing we're going to do is cut it up into a bunch of square regions called pixels. We're going to take each of those pixels. This is a black and white picture, so this is pretty easy to do. And we're going to give it a number where 255, the highest number, and there's a reason we're choosing 255, but we won't talk about that until your third class in computer science, so we're not going to worry about it today. 255 is going to represent pure white, and 0 is going to represent pure black. And every one of these pixels is going to get a number. And so our picture of Abraham Lincoln is going to be converted to a big rectangle array of numbers over here. And then I'm actually just going to flatten the whole thing out, and I'm going to make this into a simple list of numbers. Any picture you give me, I can convert into a list of numbers like this. Now, of course, I just made the problem a lot harder for humans. No matter how much you squint at this big square array of numbers, it doesn't look like Abraham Lincoln anymore. But to a computer, I've made the job a lot easier. Now, of course, I'm simplifying things just a little bit. Primarily, we want to do some processing of these numbers. For example, if I were to take this picture and make it a little bit lighter, just shade everything up. So this is not quite fully black. It's just kind of a dark gray. And this pixel is a little bit lighter gray. And the white pixels are still white, but these are maybe a little lighter, just a bit. You'd probably still be able to recognize it as a picture of Abraham Lincoln. And likewise, if I were to make it darker, you'd probably still recognize it as a picture of Abraham Lincoln. So I probably want to normalize all of my pictures and get them kind of into the same range so that one picture of Abraham Lincoln doesn't look too terribly different from another picture once I convert it into numbers. A lot of other things, of course, right? I might have one that's a little smaller. I might have one that includes more than just the headshot here. All kinds of different ways I might need to pre-process this data to kind of make it easier on my algorithm. But essentially, once I've done that pre-processing, I just take a simple conversion from pixels to numbers, and then I go on to the next step. And this is the important step for machine learning. I don't do any interpretation. I don't go in here and say, hey, this looks like an eye right here, and this looks like an eye, and I think this is sort of a nose and maybe a beard, some hair over here, maybe some ears. None of that. We just start feeding our algorithm pictures along with a label. And the label says, yes, it's a person, or no, it's not. And that's it. If I want to train this program to recognize pictures of people, I give it lots of pictures. Some are people, some are not, and I just have a yes, no label attached to each one of them. And in this training phase, the job of my program is to figure out what kinds of collections of numbers are people and what kinds of collections of numbers are not people. So how does it do it? Well, here's one of the easiest ways that it could possibly do it. This is called the K nearest neighbors learning algorithm. Now, I don't want to teach a learning algorithm that involves however many individual numbers are in here. These numbers are called the features. I've converted all of these pixels into values that we're going to call features. And the job of my algorithm is to take a collection of features and determine whether it's a person or not. But I don't want to have to look at, for you and me right now in this conversation, I don't want to have to look at hundreds and hundreds of features. So we're going to do an even simpler task. We're going to say, one that's very relevant right now, with just a very few number of features, I want to tell if somebody is sick or not, maybe so I can decide whether to let them into the grocery store or not, right? Very few number of features. So we're going to start with just two. We're going to measure somebody's body temperature, and we're going to measure their blood pressure. And then we're going to write a computer program whose job it is to determine from your body temperature and your blood pressure whether you're sick or not. To start with, we have to have training data. So we have to have a bunch of individuals where we know their temperature and we know their blood pressure, and we already know if they're sick or not. So they've been diagnosed. We know for sure from a doctor that this individual, yes, is sick, or no, they are healthy. Given that, we call it gold standard training data, we train our algorithm. And for the k-nearest neighbors algorithm, that training is as simple as plotting it in a graph or memorizing it. Essentially, we say, okay, here's an individual. This represents a human who came to the doctor's office. The doctor said, yep, you are sick. And then they put in here their blood pressure, which was fairly low. I didn't put any numbers on these scales because I didn't want to embarrass myself with inappropriate temperatures and systolic or diastolic blood pressure. So you can make them up, but we've got a fairly low blood pressure and we've got a fairly low temperature and we've got a sick individual. Another individual comes in, they're healthy. We simply put them into our plot. Here's your blood pressure, here's your temperature. Another healthy individual, blood pressure, temperature. Two features, put them into this two-dimensional space that I'm creating. Essentially, what that means is I'm memorizing every single, sorry about that, WebEx is acting up, but we'll just minimize it. I'm memorizing every single individual I've ever seen. Now, when a new person comes, now that's the training phase of this algorithm. So during the training, I simply take everyone that I've already got a diagnosis for, and I put them in here and I memorize their temperature and their blood pressure. Now we go into the time where we're going to put the algorithm online and it has to start making decisions. So how does it do it? We ask you, you come to the store and we say, oh, hey, what's your blood pressure? We measure it. What's your temperature? Here's where you fall in the graph. And then we pick a value of K. How many neighbors are we interested in? This is a 3 nearest neighbors algorithm. So I go find the 3 individuals that I've ever seen before whose blood pressures and temperatures are the most similar to yours, who are closest to you in my 2-dimensional space here. And since all 3 of them are healthy, we say you're healthy. That's our prediction. If 2 out of the 3 were healthy, we'd say you're healthy, but we're not quite as confident in that. We're going to give you a moderate thumbs up. If 2 out of the 3 are sick, we're going to say you're sick. Again, a little less confident. If you're over here, we're going to say you're not getting into the store, pal. Sorry. You clearly are in the range of somebody who is not healthy. That's it. Simple, straightforward, statistical machine learning algorithm. What if we have more features? We just scale it up. So now we've got a 3-dimensional space. So we got this little box filled with heart rate, temperature, blood pressure. We make a 3-dimensional space. We still pick our number. If I have 4 features, I make a 4-dimensional space. Of course, with a 4-dimensional space, I can't draw a picture here on my slide anymore because we can't see a 4-dimensional space, but the computer has no problem with that at all. It simply plots these things in this 4-dimensional space, figures out the closest ones and says that's my prediction. If we're going back up here to recognizing presidents, then we would have a super high dimensional space, 1 for each one of these numbers, because each person now is no longer represented by 2 numbers, temperature and blood pressure. It's every single one of these numbers, so a very high dimensional space. Well, that sounds pretty straightforward. It shouldn't take an entire semester-long class to learn how to do that. So why do we have machine learning classes, and why is it such a popular research area? Well, first of all, this is really brittle. This algorithm that I've shown you is not going to work for a lot of different kinds of data. For example, you can imagine that somebody comes in and they're healthy. So let's assume this is a 1 nearest neighbor algorithm. I'm just going to take the closest one. And so if somebody comes in and here, this dot, this red wiggly dot, is the new individual who I want to know if they're sick or healthy, I just go to the closest individual from my training data and say, oh, you're healthy because the closest was healthy. Well, if I get someone who happens to be a little bit of an outlier, they're healthy, but their temperature just runs high. That's just how they are. They're always kind of a little high temperature. Well, then what's going to happen is anybody who comes in this space here, I'm going to say they're healthy, when in fact, if I just were to take out that one individual, the dividing line between sick and healthy would be way down here. And I'm probably predicting that a lot of sick people are healthy just because of this one anomalous, unusual person. So this is brittality. We call it overfitting. And simple algorithms like this are kind of subject to that problem. So one of the things we talk about in the machine learning class is how do we resolve this overfitting problem? Let's see, we're at 3:25. I'm going to take 5 more minutes and give you just sort of a general brief idea of how one approach that we might do that. One of my research areas that is really popular right now across the whole world is deep learning and artificial neural networks. And these are machine learning algorithms that are designed to emulate, in a kind of a crude way, but designed, let me put it a different way, designed, inspired by, there's the word I want, inspired by the way that neurons work in a human brain. So a super simple picture of a neuron, you've got the cell body here, and there's a bunch of dendrites, and these dendrites of the neuron, their job is to receive signals from other neurons. They can be sensory neurons, so when you get poked with a pin, the neurons fire and they send signals to these dendrites, and maybe some of them are other different kinds of neurons. They can be motor neurons, all kinds of different neurons in the body, but the dendrites receive signals. And when enough signals are received, then the neuron fires. It creates an action potential. It sends a signal down the axon, it releases neurotransmitters, and those transmitters are then received by the dendrites across a synapse of another neuron. The key element of this is this neuron doesn't necessarily fire every time it receives one signal from another neuron. It's got a threshold. When it receives enough signals, it fires. Neural networks attempt to kind of achieve something like the kind of learning that we experience as humans when we learn with really simple computer models of how a neuron works. And these models, people think that neural networks and deep learning is a really complicated field because it does a lot of amazing things, but the model is actually incredibly simple. If I want to know if somebody's sick, I input their temperature, their blood pressure, maybe their pulse rate to these artificial neurons. The artificial neurons, all they do are a couple of really simple mathematical operations. First, they take all the inputs. The inputs are no longer neurotransmitters traveling across the synapse because we're not in biology anymore. They're numbers, a temperature, a blood pressure, a pulse. They sum them all up, and then they usually subtract something from them. They usually subtract something from them so that you can get a 0 to 1 kind of an output. So you can tell if they're above or below a threshold. And then we put it through a simple function like a hyperbolic tangent. You may have heard of that in your trig classes if you're getting ready to study computer science. Something that basically, for low values, it produces something near 0, and then it smoothly transitions up to something near 1 for high values. So it converts us into a space of 0, 1, so that the output of this is going to be close to 0 or close to 1, very few outputs in between, to tell us if you're healthy and sick. The trick to making this work is we add some weights. And so what we're trying to do is say, you know what, I figured out that if your temperature times 2.25 plus your blood pressure times 4.62 minus, got a negative weight here, your pulse times 0.74 is higher than negative 22.6, or sorry, minus 22.6 is higher than 0, then you are, or close to 0, you're healthy, and if it's close to 1, you're sick. And the trick to this is what the weights are. How do I find a set of weights that makes this answer correct? And that's where the fun comes in. That's where the math comes in. Training this thing is done the same way that we train other machine learning algorithms. We give it lots and lots of data. And every time we give it some data and say, this is an example of a temperature, blood pressure, and pulse for someone who should be sick, the algorithm updates the weights a little bit to get closer to the right output. And as we keep giving it more and more data, eventually it starts answering correctly for all of our putative patients here. The math is actually not that bad. It takes a little bit of calculus, high school level calculus, or first college class calculus. Nothing really complicated. Some basic functions, summing, and a little bit of trig, and before you know it, you've written a neural network. But the cool thing about these neural networks is not how they function, it's what they can do. So let me jump. I'm going to skip a few slides, and I'm going to hover here for just a second. If you want to play with them, here's a link where you can put together your own neural network. And if we had a little more time, I would do it, but I'm running a little bit longer than I wanted to run. So I'm going to leave this one up to you. If you go to playground.tensorflow.org, you can build your own neural network right here and watch as you try to distinguish between, let's say, healthy and sick patients or other kinds of classification problems, making decisions based on data. You can build your own and see what they're capable of. What I want to show you is what they are capable of. This is real-time operation of a computer vision neural network. This is a movie, obviously. It's not happening right now, but it was created from real-time operation. And this just blows me away because even 5 years ago, something like this would have been absolutely impossible. You can see that this algorithm is identifying people, cars, traffic lights, buses in real time. And a lot of times when they're partly occluded, it can't see the entire car, it can't see the whole person. Most of the person is blocked by another person or a car or something. The size, the perspective is changing, and yet these algorithms are capable of this remarkable task of interpreting everything that it sees in this picture. Well, not everything, 3 categories of everything with remarkable speed. And that's why they're so popular, because they've become amazingly powerful. And one of the reasons that they've become amazingly powerful is because computer scientists have come up with all kinds of cool tricks. One of the classes we teach here at Wright State University has to do with using graphics cards. The same kind of graphics card that you probably have in your computer at home if you play games, or if you've got an Xbox or a PlayStation, the same kinds of graphics hardware that's in those consoles. which is designed to do a little bit of math on a bunch of data, to take a bunch of pixels in an image and maybe multiply them all by the same amount all at once, but to do it really fast. It turns out the same kind of operations that you use to render a scene in a video game can be employed to train a complicated neural network. And so we have servers in my lab that have 2, 3, 4 video cards in them. And those cards then are used to create neural network models at the speed that we could only have done with billion-dollar supercomputers just 15 years ago. Now we can do it with a couple of 1080 Ti's from NVIDIA, which is really amazing and has opened up a lot of remarkable things. I'm going to finish up with one last example. We can also use neural networks to create. And you guys may have seen some examples of this. Neural networks can be used to to change voices, to sound like other voices, to create videos. These are some training faces, human beings that went into a neural network whose job it was to create lifelike face images. None of these individuals exist. These are all creations of something called a generative adversarial neural system, or GANs. It's a combination of two neural networks kind of playing a game against each other. And they create all of these incredibly realistic, lifelike images. None of them are actual human beings. They were all created by training a neural network. That's why they're popular, because they're very capable. Now, of course, there are some big limitations. And one of the things that we'll talk about in a machine learning class is what are the limitations. The biggest one for this, for neural networks, number one, you have to have a lot of data. Every time I put a piece of data into this thing, these weights only update by a tiny, tiny amount. And that's on purpose, because otherwise we can get brittle the same way our k-nearest neighbor algorithm was brittle. What that means is I need not hundreds, not thousands, but generally tens of thousands, sometimes hundreds of thousands of examples to train neural networks. And that's why you see neural networks that are good at recognizing speech, because there's lots of audio data out there. You see neural networks that are good at recognizing pictures, because there are lots of pictures on the internet. Neural networks for diagnosing diseases, a lot more difficult, because there's not tens of thousands of examples of people who have a particular type of cancer and people who don't have that type of cancer that you can train all of this data on, all of these networks on with that data. And so there are still some limitations. And that's one of the things researchers are working on, is how do you make these networks work with less data? If you're coming in from high school, or if you're here and you're thinking about studying machine learning, what do you need to know? Not as much as you'd think. Little basic calculus. So if you remember integrals and derivatives, mostly derivatives. We don't really work too much with integrals, mostly derivatives. If you can take a derivative of a simple function, you remember enough calculus to get started. Some basic matrix algebra, linear algebra. If you can multiply two matrices together, pretty much good to go. We can take it from there. Some basic probability and statistics, understanding what a probability distribution is. But there, we get to that in the class, the introductory class. So basically, if you've ever had a probability or a statistics class, you're probably good to get started. If you haven't, we'll introduce it to you. Got to be able to program. Python is a great choice. Almost every system that is used to train neural networks these days can be run out of Python. There are some other languages that work well as well, but Python is by far the most used one. And you got to want to work with data and do amazing things with it, because that's what this is really all about. Just a smattering of a couple of the kinds of classes that we operate, or that we offer here at Wright State. Intro to machine learning, that's where you really want to start. If you want to go in the other direction, though, and look at some of those algorithms where you're encoding information in a way that a computer can operate on, they can do a lot of things that neural networks and machine learning algorithms can't. And if we had another 30 minutes, we'd talk about those, but we've got a Foundations of Artificial Intelligence class. We touch on it, data mining. This is the parallel programming for many core GPUs class, where we talk about how to use graphics cards, GPUs, graphical processing units, to do operations other than just graphics. And so this is one of the fundamental things that has made these methods so powerful. Some of these other classes all touch on and work with machine learning and learning from data and big data and data science techniques. So I kind of have them all up there for you to take a look at. Okay, as always, I went 1,000 miles an hour and still went, 10 minutes longer than I wanted to go. But that's all right. That was kind of the objective. So now, what I want to do is, if you've got any questions for me, I haven't seen the other side of this WebEx events window. We use WebEx meetings a lot. I haven't used WebEx events, which is what we're using for this. I think you just type them into the chat. There may be a Q&A window as well that you can put them into. Either way, if you got any questions for me about machine learning, neural networks, classes at Wright State, college in general, anything that you would like to ask, I will hang here and answer any questions you've got. And if when we run out of questions, we'll call it good. And I'll put in a plug for the next one that we're going to do. Lisa, do you know who's up next week? I should have had that up and ready to go on the website, but I did not. So maybe I'll leave it to you to, oh, Dr. Cheatham has come in and mentioned that she is, which is fantastic. So Dr. Cheatham is going to be talking next week about, so the title of her title of her talk is why, and then there's a big password that basically says password but has 5s for the S's and a 0 for the O, is not a good password. This is going to be a really interesting talk. It's going to combine kind of some of the basic fundamentals of cybersecurity and algorithms into how is it that people crack passwords. If you've ever wondered when somebody breaks into a machine at Target and cracks passwords and figures out what everybody's login information is, how they do it, Dr. Cheatham is going to talk about it next week. Okay, so I have a first question, and that is this for the BA degree or the master's degree? So what I've been talking about today, in general, I've been talking about machine learning, and it's covered in both areas. At an undergraduate level, Bachelor's of Science, Bachelor of Arts, as long as you've got some programming background, you can take the Intro to Machine Learning class. You'll need data structures, and I'm not sure what the other prereqs are. We can look them up, but that class gives you the front view, and you'll learn to use some machine learning algorithms. And in fact, at the undergrad level, occasionally we have another class called Applied Machine Learning that's really kind of about just taking data and trying out a bunch of machine learning algorithms on that data set. Do that at the undergraduate level. If you decide to stay around for a master's degree, I didn't put up the graduate classes, but there's a much bigger slide that has all of the graduate classes in machine learning, artificial intelligence, data science, semantic web, and so forth. And there's even more there. To work in the field of machine learning specifically, you'll probably end up eventually going back and getting that master's degree. Most people who work in the area do, but in data science, I mean, this is an in-demand field. You can go out, and if you've studied some of these data science and machine learning courses, right out with a bachelor's degree, you can get jobs in this area. And then once you've been working at it for a while, odds are they'll send you back and say, hey, go learn more, get a master's degree, and then we'll give you the promotion after that. I am gonna, by the way, I wanna mention, I'm gonna take these PowerPoint slides and I'm gonna provide them to Ms. Morris, who will send them out to everyone who's registered for the talk, so or a link at least. So the slides will be available. And when I do that, I'll go ahead and tack in. I do have another slide of all the graduate level machine learning classes. So I'll pop them in here before I do it so that you have those available as well. Other questions on, like I said, machine learning, general college stuff, you name it, whatever you want to ask me. I am available. And if I don't see any for about 2 minutes, I'm going to wrap it up. So if you've got them, go ahead and enter them now. Just pause for a moment. Bring up the participants window. Will this event be hosted daily? Great question. We're going to do this once a week. And so it's going to be on Fridays at 3 o'clock. If you go to the computer science department page at, hold on a second. In fact, I'll tell you what, you guys can still see my screen, which is perfect. Let's go look. csc.wright.edu. If you go over to events and information, first link over here on the right, you will see, here's the mini lectures. So here's today, machine learning and big data. Next week, Dr. Cheatham why password is not a good password. After that, Dr. Doom is going to talk about digital design, one of the most popular classes that we offer here at Wright State in the computer engineering curriculum. After that, cybersecurity and so forth. So you can see all of the lecture topics here. You can register right here, and they're all going to be at 3 o'clock. Hopefully, the rest of the gang who are presenting will do a better job than I did at making them 20 minutes. That's the target. But right here at 3 o'clock for 20 minutes once a week. Looking back through to see if I've got any others. I do not see any others. Last call for any questions that you've got. And if you're visiting, if you're a high school student and you're thinking about coming, I'm happy to answer questions as well in general about Wright State, about the computer science department, about getting into college, succeeding at college, anything you've got. So I'm going to give it 60 seconds. And if I don't see a new one, we'll call it off at that point. So I'm just going to do a brief pause here for 60 seconds. Wonderful. I got a question here. So do you see machine learning, specifically neural network-based work, being an area of sustained interest among employers, i.e. should anyone worry about a bubble or the field moving quickly on to new areas of study? What a fantastic question. Thank you for that. So that is a really good question. I feel like you guys are just staring at the at my screen now. So what I'm going to do as I answer that is I am going to stop sharing so you can look at my face, which is probably far worse, but nonetheless, I can communicate a little bit. So I think that's a great question. Is it potentially a bubble? I will tell you that the broader field of data science is not going anywhere. We are just getting started. There's an amazing statistic. 98% of all, now maybe it's 90%. It's a really high percent. I should look it up before I start citing statistics. I'm going to say 90, so I'm conservative, but I think it's even higher than that. 90 or more percent of all the data in the world, every piece of data in the entire world, starting with stuff that's scratched down on papyrus and paper from the ancient times, all the data in the world, not more than 90% of it was created in the last 2 years. We're producing data at a rate that is increasing exponentially and that is vastly bigger than anything that's ever happened in the history of the world before. One of the things that we're doing right now trying to deal with this COVID-19 virus is track the data. Where are people going using cell phone data, contact management apps you've been hearing about? Where are people getting sick? Where are they not getting sick? What's the difference? All data analytics studies. That's not going anywhere. In the foreseeable future, jobs that involve interpreting data and teaching machines to automatically understand and derive conclusions from data are going to continue to be one of the most popular and important areas of all of computer science. Whether the specific kind of machine learning I'm talking about in neural networks is going to change in the next 3 or 4 or 5 years, it might. It absolutely might, because computer science, it moves fast. One of the things I actually love about this field is that it moves fast. When I came to Wright State University, I had nothing to do with neural networks. I've changed into that field because they've become a very powerful tool and something I can take advantage of for my research interests. Something new, topological data analysis. Maybe that's what's going to be the big thing 3-5 years from now. But if you study machine learning as it exists today, you'll be well situated to keep up with it as it evolves. The field of machine learning, it's not going anywhere. It's going to continue to be very in demand among employers because the data economy is the biggest and fastest growing economy in the world right now. And it's not going to change. Understanding data is something that makes companies a lot of money. And so they're going to want to have more and more capability to understand and interpret data. Great question. Thank you for that. Okay, any others? One more time. I'm going to give it 60 seconds, and then I'm going to say going once, going twice. Great question. Thank you. So the question I have is, would I need to know matrix algebra, calculus, and all the other courses that you talked about before college, or will it be covered in college courses? It'll be covered. You can come in kind of at lots of different levels. And when you come in to the university, we usually give you a math placement test, and we kind of put you right where you can pick up from where you left off in high school. And so you'll pick up where you left off. Machine learning is what we call a technical elective in computer science, which means before you get there, you got to take a couple courses in programming. You got to take a course in computer hardware called computer organization. You got to take a data structures course. It's going to be 3 or 4 semesters worth of courses. At the same time, you'll be taking discrete math. You'll be taking a little bit of matrix math, and you can take any calculus that you need to take. So there's no rush. If you happen to have it, if you've had AP Calculus or a calculus class in high school, fantastic. You're on the fast track. If you haven't, no problem. You'll pick it up. And the thing that I wanted to talk about the math for specifically was I really wanted to make the point that it shouldn't scare you, that we're not talking about rocket science for the math that we do. We're talking about stuff that's very doable. So if you're coming in wherever you're at, we'll pick it up from there. And you can learn the math that's necessary and the other parts of programming and other things that you need, and then start working on the machine learning side of things. Great question so far. Do I have any more? One of the things you have to be really good at as a professor is handling awkward silences. So that when you say, any questions, you got to be able to stare down everyone in the class and wait till someone asks one. So we'll have a nice awkward silence for a minute. And I'm not seeing any. So I'm going to move towards wrapping up. This has been a lot of fun. I hope that you have enjoyed it. And I got one last one that I'm going to answer before I wrap up, and it is, do I teach any of the machine learning courses? I haven't in a while, but we're reshuffling all the time course teaching. So there's a very decent chance that I will be teaching a machine learning course sometime in the next year or two. I hope so, because I love it and I like teaching it. But if not, one of the other outstanding faculty here in the department who works in this area we will definitely be offering them. I can't say for sure who'll be teaching them, but they will definitely be on the books. This is a great question. The question is, back to the neural network, is there any problem if you give the algorithm too much training data? What a fantastic question. So it turns out you can never have too much data. More data always helps you to understand the problem better. But there are lots of different problems that can come up in training these kinds of algorithms. You can train them for too long. You can train them for not long enough. You can train them with the wrong data. One of the biggest problems, for example, is data that's not well balanced. If we're actually trying to give an algorithm, train it to diagnose a particular disease, there are always going to be many, many, many more people who come into a doctor's office who don't have esophageal cancer, for example, than who do. And that's, of course, a good thing, but it means that we don't want to throw away data. So if we use all the data we have, we might have tens or thousands of examples of negative examples, not cancerous cells, and only dozens of examples of cancerous cells. And the way we use that can influence our algorithm. And in fact, something you may have heard of in the news not too long ago is that algorithms can develop biases. If we're not careful about the data that we give to our algorithms, algorithms can develop, just like humans can, stereotypes and biases. And when you're talking about an algorithm, for example, that makes loan decisions, that can be very important. So picking the right data is generally a very important part of the process. But in general, and I'm speaking in broad generalities right now, is more data is generally better. It helps the algorithm to have a better understanding of the problem, but we have to be careful about what we do with it. Okay, now I'm checking the Q&A. I don't see any more there. I am checking the chat and I don't see any more there. Let me say that we will follow up with everyone who registered with a quick email. In that email, we'll have how to get to the slides from the talk today, how to contact me, and how to contact the department. If you have any other questions, interests, or want to follow up in any way, of course, we'll get back to you and follow up with you. So with that, I want to say thank you very much for joining us this afternoon. It's been a lot of fun. I hope you found it interesting and entertaining, and maybe now have a little bit more of an interest in taking a class in machine learning. And if everything goes just right, maybe I'll see you in the classroom someday soon talking about a topic that we've talked about today. All right. Thanks, everyone. Bye-bye.